Algebra by Michael Artin. Chapter 2, Groups. 1. The definition of a group. In this chapter, we study one of the most important algebraic concepts, that of a group. A group is a set on which a law of composition is defined, such that all elements have inverses. The precise definition is given below in 1.10. For example, the set of non-zero real numbers forms a group Rx under multiplication. The set of all real numbers forms a group R plus under addition. The set of invertible n by n matrices, called the general linear group, is a very important example in which the laws of composition is matrix multiplication. We will see many more examples as we go along. By the law of composition on a set S, we mean a rule for combining pairs A, B of elements S to get another element, say P, of S. The original models for this notation are addition and multiplication of real numbers. Formally, the law of composition is a function of two variables on S, with values in S, or it is a map, Cartesian product S cross S mapped to S, or A, B mapped to P. Here, S cross S denotes, as always, the product set of pairs A, B of elements of S. Functional notation P equal F of A, B isn't very convenient for laws of composition. Instead, the element obtained by applying the law to a pair A, B is usually denoted by a notation resembling those used for multiplication or addition. P equal AB, A cross B, A after B, A plus B, and so on. The choice being made for the particular law in question. We call the element P the product or sum of A and B, depending on the notation chosen. Our first example of a law of composition, and one of the two main examples, is matrix multiplication on the set S of n by n matrices. We will use the product notation AB most frequently. Anything we prove with product notation can be written using another notation, such as addition. It will continue to be valid because the rewriting is just a change of notation. It is important to note that the symbol AB is a notation for a certain element of S. Namely, it is an element obtained by applying the given law of composition to the elements called A and B. Thus, if the law is multiplication of matrices, and if A equal the matrix 1, 3, 0, 2, and B is equal the matrix 1, 0, 2, 1, then AB denotes the matrix 7, 3, 4, 2. Once the product AB has been evaluated, the elements A and B cannot be recovered from it. Let us consider a law of composition written multiplicatively as AB. It will be called associative if the rule, 1.1, quantity AB times C equal A times the quantity BC, holds for all A, B, C in S, the associative law, and commutative if, 1.2, AB equal BA, holds for all A, B in S, commutative law. Our example of matrix multiplication is associative but not commutative. When discussing groups in general, we will use multiplicative notation. It is customary to reserve additive notation A plus B for commutative laws of composition. That is, when A plus B equals B plus A for all A, B. Multiplicative notation carries no implication either way concerning commutativity. In additive notation, the associative law is the quantity A plus B plus C equals A plus the quantity B plus C. And in functional notation, it is F of A, B, C equals F of A, F of B, C. This ugly formula illustrates the fact that functional notation isn't convenient for algebraic manipulation. The associative law is more fundamental than the commutative law. One reason for this is that composition of functions, our second example of a law of composition, is associative. Let T be a set and let G, F be functions or maps from T to T. Let G after F denote the composed map, T mapped to G of F of T. The rule G, F maps to G after F is a law of composition on the set S equal maps t comma t of all maps from t to t. As is true for matrix multiplication, composition of functions is an associative law, for if f, g, h are three maps from t to itself, then the quantity h after g after f is equal to h after the quantity g after f. This is clear since both composed maps send t to h of g of f of t. The simplest example is that T is a set of two elements, A, B. Then there are four maps from T to T. Iota, the identity map defined by iota of A equals A, iota of B equals B. Tau, the transposition defined by tau of A equals B, tau of B equals A. Alpha, the constant function alpha of A equals alpha of B equals A. Beta, the constant function beta of A equals beta of B equals B. The law of composition on S can be exhibited by a multiplication table as follows. Iota tau alpha beta, tau iota beta alpha, alpha 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 alpha, beta 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 beta, which is to be read in this way, U after V. Thus, tau after alpha equals beta, while alpha after tau equals alpha. Composition of functions is not commutative. Going back to the general law of composition, suppose we want to define the product of a string of n elements of a set. A sub 1, a sub 2, a sub n equal ? There are various ways to do this using the given law, which tells us how to multiply two elements. For instance, we could first use the law to find the product a sub 1, a sub 2, then multiply this element by a sub 3, and so on. The quantity a sub 1, a sub 2 times a sub 3 times a sub 4, When n equals 4, there are four other ways to combine the same elements. The quantity a sub 1, a sub 2 times the quantity a sub 3, a sub 4 is one of them. It can be proved by induction that if the law is associative, then all such products are equal. This allows us to speak of the product of an arbitrary string of elements. 1.4 Proposition. Suppose an associative law of composition is given on a set S. There is a unique way to define, for every integer n, a product of n elements, a sub 1, a sub n, of S. We denote it temporarily by a sub 1, a sub n, with the following properties. 1. The product a sub 1 of one element is the element itself. 2. The product a sub 1, a sub 2 of two elements is given by the law of composition. 3. For any integer I between 1 and n, the product a sub 1 through a sub n is equal to the product a sub 1 through a sub I with the product a sub I plus 1 to a sub n. The right side of equation 3 means that the two products a sub 1 a sub I and a sub I plus 1 a sub n are formed first, and the results are then multiplied using the given law of composition. Proof. We use induction on n. The product is defined by 1 and 2 for n less than equal to 2, and it does satisfy 3 when n is equal to 2. Suppose that we know now how to define the product of R elements when R is less than equal n minus 1, and that this product is the unique product satisfying 3. We then define the product of n elements by the rule the product a sub 1 a sub n is equal to the product a sub 1 a sub n minus 1 times the product a sub n, where the terms on the right side are those already defined. If a product satisfying Rule 3 exists, then this formula gives the product because it is Rule 3 when I equals n minus 1. So if it exists, the product is unique. We must now check Rule 3 for I less than n minus 1. The product a sub 1 through a sub n equals the product a sub 1 through a sub n minus 1 times the product a sub n. Our definition equals the quantity, the product a sub 1 through a sub I times the product a sub I plus 1 through a sub n minus 1 times a sub n. Induction hypothesis equals the product a sub 1 through a sub I times the quantity a sub I plus 1 through a sub n minus 1 times the product a sub n. The associative law equals the product a sub 1 through a sub I times the product a sub I plus 1 through a sub n. Induction hypothesis. This completes the proof. We will drop the brackets from now on and denote the product by a sub 1 through a sub n. An identity for a law of composition is an element E of S having the property that 1.5 EA equals A and AE equals A for all a member of S. There can be at most one identity element. For if E and E prime were two such elements, then since E is an identity, E prime equals E prime. And since E prime is an identity, E prime equals E. Thus, E is equal E prime. Both of our examples, matrix multiplication and composition of functions, have an identity. For n by n matrices, it is the identity matrix I, and for maps of T to T, it is the identity map, which carries each element of T to itself. Often, the identity is denoted by 1 if the law of composition is written multiplicatively, or by 0 if it is written additively. These elements do not need to be related to the numbers 1 and 0, but they share the property of being identity elements for their laws of composition. Suppose that our law of composition has an identity, and let us use the symbol 1 for it. An element A member of S, is called invertible if there is another element B such that AB equals 1 and BA equals 1. As with matrix multiplication, Chapter 1, 1.17, it follows from the associative law that the inverse is unique if it exists. It is denoted by A inverse. A inverse equals A inverse A equals 1. Inverses multiply in the opposite order, 1.6. The quantity AB inverse is equal to B inverse times A inverse. The proof is the same as for matrices. Chapter 1, 1.18. Power notation may be used for an associative law of composition. 1.7. A to the n power equals A n times for n greater than equal to 1. A to the 0 power equals 1, provided the identity exists. A to the negative n power equals A inverse A inverse, provided A is invertible. The usual rules for manipulation of powers hold. 1.8. A to the r plus s power is equal to A to the r power times A to the s power, and the quantity A to the r power to the s power is equal to A to the rs power. It isn't advisable to introduce fraction notation, 1.9, b over a, unless the law of composition is commutative, for it is not clear from the notation whether the fraction stands for b times a inverse or a inverse times b, and these two elements may be different. When additive notation is used for the law of composition, the inverse is denoted by negative a, and the power notation a to the n power is replaced by the notation na equals a plus ... plus a, as with addition of real numbers. 1.10 Definition. A group is a set G together with a law of composition which is associative and has an identity element, and such that every element of G has an inverse. It is customary to denote the group and the set of its elements by the same symbol. An abelian group is a group whose law of composition is commutative. Additive notation is often used for abelian groups. Here are some simple examples of abelian groups. 1.11. Z plus, the integers with addition. R plus, the real numbers with addition. Rx, the non-zero real numbers with multiplication. C plus and C times, the analogous groups where the set C of complex numbers replaces the real numbers R. Here is an important property of groups. 1.12 Proposition. Cancellation law. Let A, B, C be elements of a group G. If AB equals AC, then B equals C. If BA equals CA, then B equals C. proof, multiply both sides of AB and AC by A inverse on the left. B equal A inverse AB equals A inverse AC equals C. Multiplication by A inverse in this proof is not a trick. It is essential. If an element A is not invertible, the cancellation law need not hold. For instance, 0.1 equals 0.2, or the matrix 1 space 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 times the matrix 1 space 2 1 equal the matrix 1 space 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 times the matrix 1 space space 3. The two most basic examples of groups are obtained from the examples of laws of composition that we have considered: multiplication of matrices and composition of functions, by leaving out the elements which are not invertible. As we remarked in Chapter 1, the n by n general linear group is the group of all invertible n by n matrices. It is denoted by 1.13. GL sub n is equal to n by n matrices A with the determinant of A not equal to 0. If we want to indicate that we are working with real or complex matrices, we write GL sub n of R or GL sub n of C according to the case. In the set S maps from T to T of functions, a map F mapping T to T has an inverse function if and only if it is bijective. Such a map is also called a permutation of T. The set of permutations forms a group. In example 1.3, the invertible elements are iota and tau, and they form a group with two elements. These two elements are the permutations of the set A, B. The group of permutations of the set 1, 2, n of integers from 1 to n is called the symmetric group and is denoted by S sub n. 1.14. S sub n equal the group of permutations of the set of 1 through n. Because there are n factorial permutations of a set of n elements, this group contains n factorial elements. We say that the order of the group is n factorial. The symmetric group S sub 2 consists of the two elements iota and tau, where iota denotes the identity permutation and tau denotes the transposition which interchanges 1 and 2, as in 1.3. The group law composition of functions is described by the fact that iota is the identity element, and by the relation tau equal tau squared equal iota. The structure of S sub n becomes complicated very rapidly as n increases, but we can work out the case n equal 3 fairly easily. The symmetric group S sub 3 contains 6 elements. It will be an important example for us because it is the smallest group whose law of composition is not commutative. To describe this group, we pick two particular permutations, x, y, in terms of which we can write all the others. Let us take for x the cyclic permutation of indices. It is represented by the matrix 4.3 from Chapter 1. 1.15. X equal the matrix 0, 1, 0, 0, 0, 1, 1, 0, 0. For y, we take the transposition which interchanges 1 and 2, fixing 3. 1.16. Y equal the matrix 0, 1, 0, 1, 0, 0, 0, 0, 1. The 6 permutations of 1, 2, 3 are 1.17. The set 1, x squared, y, xy, x squared y, which is equal to the set of x to the I power y to the j power, such that I is greater than equal to 0 and less than equal to 2, and j is greater than equal to 0 and less than equal 1, where 1 denotes the identity permutation. This can be verified by computing the products. The rules, 1.18, x cubed equal 1, y squared equal 1, yx equal x squared y, can also be verified directly. They suffice for computation in the group S sub 3. Any product of the elements x, y, and their inverses, such as x inverse y cubed x squared y, for instance, can be brought into the form x to the I power y to the j power with I greater than equal to 0 less than equal to 2 and j greater than equal to 0 less than equal to 1 by applying the above rules repeatedly. To do so, we move all occurrences of y to the right side using the last relation and bring the exponents into the indicated ranges using the first two relations. X inverse y cubed x squared y equal x squared y x squared y equal x squared quantity yx times xy equal x squared y xy equal equal x to the sixth power y squared equals 1. Therefore, one can write out a complete multiplication table for S sub 3 with the aid of these rules. Because of this, the rules are called defining relations for the group, a concept which we will study formally in Chapter 6. Note that the commutative law does not hold in S sub 3 because yx is not equal to xy. Algebra by Michael Artin, MIT. This book was published in 1991 by Prentice Hall. It is read by Jim Renholt with programming and illustration by Jim Renholt, 2019. Thank you for listening.